So chapter 5 was a brief introduction to initial value and boundary value problems and some numerical methods for solving the boundary value problem. We'll directly now move to large-scale ocean circulation and look at the derivation of the equations of motion and see what are the various modeling issues involved and how we go about solving the equations and what the equations are. So let's first define the concept of material derivative. I think most of you have probably heard of it if you had some partial and ordinary differential equations. So it's referred to as Lagrangian derivative, material derivative, and total derivative, as opposed to the Eulerian derivative. So if we have position vector for any particle of water, or we could be looking at something else like velocity, salt, salinity, temperature, density, whatever. So it's defined in time r as a vector in x, y, and z, and they are all changing in time as well because the particle is moving around and you are following the particle. That's what makes it Lagrangian or material, as opposed to Eulerian, where you are sitting at a point and seeing things go by. So straight away we can derive the speed with which the particle is moving in each direction. So the vector ut is the time derivative of rt divided by t. So we can look at it as dxt dt plus dyt dt and dzt dt. So that's equal to ut, vt, and wt. Okay, so how do we go about writing the same material derivative for note that we are calling it d dt here. It's not partial, so just remember. Okay, so that's the total derivative as well. If you take any particular quantity like temperature, salt, density, and so on, as I mentioned before, it's better to think of this as a position vector and the velocity vector. So here dA dt is then partial the time rate of change of a at a given point plus dx dt, because position itself is changing, times dA dx, how the value of a is changing in the x direction, dy dt times partial dA dy plus dz dt, dA dz. Okay, so we are doing dA dt, which means we do dA dt times sorry, dA dx times dx dt, dA dy times dy dt. I think you know how this partial rule of partial differentiation works. So when we do partial a, partial t, obviously we are holding x, y, and z constant, which means it's at a fixed location. So here is the key difference between the material derivative, total derivative, or the Lagrangian derivative, and the Eulerian derivative. Eulerian derivative is modified by the movement in space and the gradients that occur in space. So temperature gradient in x, y, and z, for example, and how it is moving with the fluid in terms of dx dt, dy dt, and dz dt together is going to modify the time rate of change at a given location if you follow the particle. So that gives us total derivative. I hope it's clear. I think you've done this before somewhere. So if we take then the Lagrangian derivative or material derivative dA dt written this way, then we can write this as partial dA dt plus vector uvw dotted with dA dx, dA dy, dA dz, the gradients of the quantity you're looking at, density, temperature, salt, or whatever else, and this can be abbreviated to dA dt plus u dot grad dA, where we are using vector notations with the dot product. Okay, we can then move to deriving equation of motion with this knowledge, and we jump straight away to the Newton's second law of motion, F equal ma. So we are doing it for a unit mass, so we can write du dt equals a plus AI. So this is the sum of all real forces, and this is the sum of all apparent forces. And because we are on a rotating framework, you know that immediately we are going to have apparent forces, which obviously are Coriolis effects. So AI here then can be written as minus 2 omega cross u minus omega cross r. So this is the Coriolis deflection, apparent force, apparent acceleration. This is the centrifugal force you feel because you're on a rotating planet. We are not deriving this here, but I have podcasts elsewhere on Coriolis in the dynamics course, for example, where you can look at the details of how we derive this. So you have real accelerations and apparent or imaginary forces. So we do this in a local Cartesian coordinate on a rotating sphere that gives us some simplifications to the to the equations we have to look at. So we have the meridional direction or the latitudinal direction and the longitudinal direction. So this sweeps in 0 to 360, and this goes typically from 0 to 90, right? Latitudes go from the equator to the pole. What we do is take the radius of the Earth, and we are solving everything on the surface. So here is our local x, y, z coordinate, so local Cartesian coordinate. So we need to project the Coriolis effect onto this local Cartesian plane, and we end up with either an F-plane where the Coriolis remains constant, or a beta plane where we will see in a minute that means that the beta is the derivative of Coriolis with latitude. So the Coriolis depends on latitude, which is much more realistic, even though it's a linearization, because Coriolis is 0 on the equator but increases towards the pole and reaches its maximum at the pole. In fact, it is this centrifugal force that moves the Earth's continent and mass, because it's not a solid rock, and it has fluid inside and asthenosphere and so on. The centrifugal force pulls the Earth near the equator and squishes the sphere into an ellipsoid. So we have the semi-minor axis in from the center of the Earth towards the poles, giving us 6,003 I cannot even read it. 63,500 meters. So it should be 6357, 6,000 some kilometers. So divide by 1,000, you know what. So the difference in the radius at the equator to the pole is about 21.4 kilometers or so. That's how much the Earth has been squished. And obviously that means if you imagine a plumb line that is hung in the middle of a rotating table, it will be offset because of the gravitational pull and the rotational effect. That's kind of what we do to get the horizontal component of the centrifugal force to go with the horizontal component of gravity on the sphere, and basically it's very small. So the horizontal component of the centrifugal force is small. It's the vertical component that goes in the direction of gravity, and the rotational effect is what we are going to be left with. So Coriolis acceleration then can be written as minus 2 times 0 omega cosine phi in the x direction, in the x direction, y direction, z direction. So crossing with u, v, w, that's what is this term here, 2 omega cross u. So that is minus 2 omega sine phi v. You know how to do the matrix operation. Minus 2 omega sine phi u. And 2 omega cosine phi u. So x component, y component, and the z component. And because these tend to multiply uv and w when you are doing Coriolis effects. W is typically very small because we are assuming Earth, the radius is large, and the envelope of the ocean and atmosphere that are on the surface for which we are doing the equations of motion. The horizontal scales of motion are much larger than the vertical scales because it's a thin shell. Atmosphere and ocean are a very thin shell, order a few kilometers in the ocean and order 10 kilometers in the atmosphere. So we can ignore the vertical component of the Coriolis effect, which gives us Coriolis F is basically 2 omega sine phi, and that gives us deviations in the horizontal because of the rotational effect or the Coriolis effect. Okay, we end up simplifying it as often at the equator plus the gradient in the latitudinal direction and the latitudinal difference. So this is basically f50 plus df d phi. Because f is only a function of latitude, we can write this as total derivative with at phi 0 times delta phi minus phi 0, which you can expand in terms of 2 omega sine phi 0 and write f at any latitude phi as f0 at the equator plus beta y. So, or f0 at the domain you are looking at in its center and around it. So if you're at some latitude, f0 would be here, and you would do a beta plane in the plus minus y direction as beta y around its mean value here. So that's the beta plane. So if you assume f is constant and f0, then you are on an f plane. But if you assume f varies with y, which is realistic, then you do it as f0 plus beta y. Of course, you are still approximating as a local Cartesian coordinate because you're taking the linear derivative at y, the local derivative. Okay, so we will leave that there and then come back and derive the forces that act on a parcel, so that we can go back to F equal ma and write our equation of motion for a parcel of water, and then derive the equations for large scale ocean circulation. And then we get to make other approximations like the shallow water approximation to derive some equations which we will solve to show how climate modeling works. Okay.